Okay, so we'll get going here. Appreciate everybody joining us today. This is our second virtual meetup, and we are going to continue having these until we feel a little safer from the disastrous COVID-19 risks. So we'll continue having them here and post our videos on YouTube for watching later as well. So I think this is a good interim solution for all of us. And I appreciate great speakers like Guy here to come and present for our group. So today's, we have a great presentation lined up for you. Dungeons, Dragons, and Graph Databases, presented by Guy. Guy works for Redis Labs as a developer advocate, combining his decades of experience in writing software with positions for sharing what he, passion for sharing what he learned. Guy goes out into development communities and helps others build great software. Teaching and community have long been a focus for Guy. He is the president of the Columbus JavaScript user group and organizer for Columbus Functional Programmers, and has even taught programming at a prison in Central Ohio. That's
true story.
Really impressive. In his personal life, Guy is a hard-boiled geek interested in role-playing games, science fiction, and technology. He has also slightly less geeky interest in history and linguistics. In his spare time, he volunteers for the local Cub Scout pack, goes camping, and studies history and linguistics. Guy also lives in Ohio with his wife and his teenage sons, and an entire wall of games, which I think I see right there.
Yeah, there it is.
Wonderful.
But in all fairness, there's also a lot of science fiction novels up there. So
nice, nice. Okay, take it away, Guy.
Okay, so yeah, thanks everyone for coming out tonight. So you know, we're a relatively small group. We're not. It's not like I've got scores of people here that we're talking. So during the talk, feel free to just ask me a question if you have a question. Just unmute yourself and ask. You know, if you want to wait till the end, you can wait till the end as well. But I'm perfectly happy with a more casual conversational tone for the talk tonight. So let's get my screen shared. That's probably a good place to start, isn't it?
Absolutely.
Okay, there we go. You can now see a default Mac background. Hooray. Let's get something a little more interesting. There we go. That's more interesting. So hang on, let me get everything positioned just right. There we go. It's like he's doing things. I don't know what he's doing. He's just talking and saying things are good. I'm getting the little zoom window with the faces in a place where I can see them. So so this is my talk, Dungeons, Dragons, and Graph Databases. I like all of these things, and so I thought I'd put a talk that brought them all together. I've already been introduced as Guy Royse, developer advocate at Redis Labs. The really relevant bits of information here are the little social media links down there. I always appreciate a follow on Twitter, but the thing that you actually care about is going to be github.com/Guy Royse. That's where all the code that I'm going to show you is going to reside. Actually, a link to the slides is out there as well. So that's the relevant thing. If you go to guy.dev, that's my domain name. I got guy.dev, which is I mean, that was a coup, wasn't it? Although at one time I was telling someone I got guy.dev because I was pretty proud of it at the moment, and she didn't know that my name was Guy. And she's like, why would you want guy.dev? I'm like, no, it's my name's Guy. It's for Guy, the developer, not for Guy developers. Yeah. so it's guy.dev as in Guy Royse, right? So, but yeah, but if you go there, you'll see that I haven't updated my blog in about 16 months. So nothing to see there, move along. You know, I'm a big fan of Dungeons and Dragons. And so I thought, since this is a D&D themed talk, I should probably include my character sheet. So here's my character sheet. I'm a neutral good dwarven bard. Bard seemed like the closest thing to developer advocate. You know, it's, you know, you go out there, you're performing a little bit, right? Like I'm doing right now. I got some armor classes and hit points. Those don't really matter because I never get in any fights. And then I got my stats over here. You can see that I have an intelligence of 8 and a wisdom of 8, but a charisma of 16. So that tells you that this talk is going to be all sizzle and no steak. It's going to be full of fun and no substance. I don't actually know things. I just mimic knowing things. But so this is my character sheet, right? And as a player of Dungeons and Dragons, I have a problem. I want to level up my character and I want to get gold because I need to improve my gear, right? I need to maximize my DPS. I guess in D&D it would not be damage per second, it'd be damage per round maybe, or damage per attack. But I want to maximize that. And in order to do that, I need to get treasure, I need to get experience. And I need to go to the dungeon to find these things. But the dungeon's kind of a hard to navigate space. I need to find the best path through the dungeon so that I can get there the quickest and get either the gold or the experience or whatever I need. I need to navigate that dungeon quickly. I need to find the path through the dungeon, which rooms connect to which rooms. They take me to the best monsters with the best treasure so that I can be a total D&D munchkin. And I thought, well, I don't need to do this the hard way. I'm a developer. I could write a program that does this for me. I could build a relational database. I could have a rooms table, and I could have a treasures table, and I could have a monsters table. I could create relationships between them. And then if you start thinking about, though, I want to find a path through this dungeon, how do I write that query? And so I could use a relational database, or I could use a graph database. And so instead of having tables, I've got nodes with connections. And so what I'm going to do in this talk is I'm going to explore both ways of solving this problem with a graph database and with a relational database. So if you're familiar with graph database or relational databases, which, quick show of hands, who hasn't used SQL before, right? Everyone's touched SQL. It's the only language that I learned in college that I still use semi-regularly. But you probably, or it's a good chance you haven't used a graph database, or you haven't really gone very deep into them. And so I'm going to use the relational example and then show you how you do it in graph. And then I'm going to show the things you can do in graph that you can't do in relational easily. And for all my examples, I'm going to use Redis Graph. Redis has a module that extends it to add graph capabilities. So my examples all run on that. And yeah, that's our rough plan for tonight. Sound good? Cool.
Great. Let's do it.
Okay. So the first question is, what the heck's a graph database? Right. Some people might be wondering what a graph database is. Well, there's a question behind that, which is, what's a graph? I'm not a person with a heavy math background at all. And so I never studied graph theory in college. I didn't learn calculus. I didn't even learn linear algebra until about 5 years ago. And so I didn't learn what a graph was. And so I had to figure it out. I find myself thinking about graph databases and machine learning, and I don't have this math background. It's just this thing that tends to happen. And so I have to try and get like an intuitive understanding of these things to present on them. So you may not have been exposed to what graphs are either, but graph is a series of nodes connected by relationships, or a series of vertices connected by edges. This die 20 that we see right here is a graph. It happens to be a Platonic solid as well. It's got a vertex. That's the point, right? That's this part of the D20 right here, right? And it's got edges which connect those vertices together. And so this is a very simple graph. It's a very symmetrical graph too, actually. But it's an example of a graph. Graphs, however, don't have to describe shapes, and they don't have to describe three-dimensional Platonic solids like a 20-sided die or a 4-sided die. They could be more abstract than that. The simplest graph actually has no vertices and no connections. That's called a null graph. This is a null graph. It's a blank page. Right? Not really much here, right? There's actually some debate among people that have PhDs in mathematics whether a null graph is technically a graph or not. And I kind of don't care because they're not useful in terms of graph databases. So, but some people argue about things like that. It's kind of like saying whether you should have nulls in a programming language or not, or should you have what do they call them in Swift? I can't remember. It's not nullable, but there's a type that whether an object can have a value of null or not. And I think .NET has something similar, but I can't remember what it is. But anyhow, so that's a null graph. We've got, let's make this null graph a little more interesting. Let's add some nodes to it. So now we've got some nodes. There's no relationships between these nodes. So we got a bunch of vertices, but no edges. And that's a perfectly valid graph. Here we've got nodes A through G, and they're just kind of hanging out there in space. They're doing their thing. It's a little more interesting, but it could be even more interesting because you could add some edges, some relationships between them. And so now this graph has some relationships. A is related to C and D. G is related to C. B and F are related to each other. E is still out there all by its lonesome. And in fact, because this graph isn't connected, completely connected together, there's nodes that are separated out from each other. It's actually referred to as being isolated, not the whole graph, but like the nodes that aren't connected to the other nodes are isolated from each other. So node E is isolated. Nodes B and F are actually isolated as well. They have a relationship, but they're not connected to all the nodes in the graph. And even the big set in the middle is isolated as well. Excuse me. And so this is just a way of talking about these graphs. It's a terminology. And so if part of the graph doesn't have a path that leads to another part of the graph, it's isolated. If we go ahead and connect everything together, we now have a connected graph. And what this means is that any node has a path to any other node. So there aren't nodes that you can't get to. And the example I'm going to use tonight is a fully connected graph. They don't have to be fully connected, or they don't have to be connected. You can do fully connected as well. That's slightly different. Fully connected means every node connects to every other node. So think of it, you see those little diagrams, this is the star that's got all the networks connecting together, showing this node connects to all the other nodes in the network, and this node connects to all the other nodes in the network. That's a fully connected graph. The other thing about this graph so far is that it's undirected. And what that means is that A is related to B and B is related to A. There's a connection or a relationship there, but there's not any, there's no direction to it. It's A is not connected to B, but in a particular direction. There's no directionality. But directionality is easy to add. You just use arrows. And so now these relationships have a little bit of extra information associated with them. They're showing the direction of a relationship. And you can think of these nodes like A is related to B, but B is not related to A. Or maybe it's like if you think about it genealogically, my mother beget me. And so that's showing there's a direction to that relationship between a parent and a child. And so this arrow is representing that sort of direction on that relationship. It's hard to describe this without using the word direction, but it's actually a really intuitive concept at the same time. Other things we can say about graphs is we can talk about their degrees. We talk about the degrees of the nodes in the graph specifically. So node A has a degree of 3, and that's because it has 3 relationships. It's related to D, C, and B. You can also say out and in degrees with directed graphs. So node B has an out degree of 2 because it has 2 outgoing relationships, has 1 incoming relationship. If you have an incoming relationship, that's your in degree. So like the node E there has an in degree of 1, an out degree of 0, and a total degree of 0 or of 1. And so this just, again, this is terminology to talk about graphs and how the nodes relate to each other. And graph databases can do all of these structures. And there's really no rules about how these relationships can happen, right? We've got this nice, neat 2-dimensional layout here showing that nothing crosses, but there's no reason D can't connect to B and cross over that line in the middle. I mean, it doesn't have to fit on a 2-dimensional piece of paper. They're just relationships. In fact, The same nodes can connect to each other in multiple directions. So here we have A and C, and A and B are connected to each other both directions. A is connected to itself. B is only connected to C, but not the other way around. And so you can almost think of these as like one-way streets and two-way streets. And so there's really no rules about how these things connect together. So that's sort of a graph intent in 5 minutes. Right? There's much more to it, but this is enough for what we need to know for a graph database. Actually, probably slightly more than we need to know. To make a graph database, what you do is you lay data on top of that graph structure. So here we've taken the nodes and we've given them types. These nodes aren't the same. Some of them represent rooms, some of them are representing treasure, some of them are representing monsters. And those nodes that represent monsters and treasures and rooms can have data associated with them. So here we have Alice the elf and Bob the ogre are the two monsters. If I was looking to maximize my XP, I'd probably want to go after Alice the elf first, because Alice is a CR7 with 350 experience points. But if I wanted to go after treasure, then going after the treasure in the bottom right there with an ID of 6, that's a 1,250 gold piece +1 sword. That sounds like the way to go. And nothing's guarding it. And so, but we're adding data with these nodes. These are just attributes. You'll see they got a type, monster, room, treasure. That's a type or a label. Label is probably a better word to describe that. And then there's attributes that we added, like ID and name and experience point and challenge rating and gold piece value. And so this is the data that we can overlay over our nodes. We can also lay data over our relationships by giving them a type. So the room ID1, the statue room, every good dungeon starts with the statue room, right? Has a contains relationship right here, right? A monster, Alice the elf. And room 1 leads to room 3, and room 3 leads to room 1. And so you've got these relationships that also have data on them. So it's kind of a neat way of representing your data. It's very different from a relational database. And what you end up with is this nice database, this nice graph that has all the data about our dungeon. I already talked about nodes and relationships, but this is sort of summarizing what we've talked about so far. Nodes or vertices represent items. They tend to be nouns. And they can have a label like monster or treasure, and they have attributes like name and value. And like in a graph database, those nodes can stand by themselves. They don't have to be related to anything. So you could just have a graph database full of rooms, and you could go query them. The relationships represent the connections between the nodes. And they connect 2 nodes, and they always connect 2 nodes. That's all they do. And in fact, if you get rid of one of those nodes, the relationship goes away. So the relationship doesn't exist if the nodes don't exist. So like if you're using SQL, you would, if you want to delete an entry in say you got a one-to-many relationship in a relational database, and you want to delete the one relationship, you have to go in and delete all the many relationships first, and then delete the one. Otherwise, you've got these orphaned records out there, or if you've got referential integrity enforced in your database, it'll actually keep you from doing it. Here, if you delete either node, the relationship just goes away automatically. Relationships have a type, which is just a string, and they have a direction. And they can have attributes like rooms do as well. Like the leads to here, I have showing a distance of 45, that'd be in feet. I found that if I want to put attributes on my relationships, that usually means I'm doing the wrong thing, because that means it's starting to behave like a node. And so I tend to steer away from that. And so I won't show that in this particular example, but that is a thing you can do as well. And the relationships kind of read like a sentence. Like the room contains a monster. The rooms are the room is the noun. The relationship is a transitive verb, and then the monster is the direct object. The room contains a monster. Now you don't have to do it this way. You could actually set things up the other way. Say the monster is contained by a room. and the directionality could point the other direction, and it still works. Everything still works the same. But as my English teacher told me, the passive voice is to be avoided. So by zombies. This is how I kind of think about it. If I can make a sentence out of the relationships in my graph, it sort of like tells me I'm setting it up right. It's the way. It's kind of a smell. If it doesn't read well, then I might be going down a bad path. So, make sense so far? Cool, good. Enough theory. We need to do real things, right? Right. So we still have the problem, right? I still don't know how I'm going to find the best rooms with the best monsters and the best treasure. And we do know that we want to solve this with a relational database, and we want to try and solve this with a graph database. But how do we do those things, right? Well, we probably already know how to do that with a relational database, right? We're going to use SQL. That allows us to create our tables, query them. It's the thing that we've been using our entire careers, right? There is an analogous sort of language for graph databases. It was made popular by Neo4j, created by Neo4j actually, that Redis Graph makes use of as well, called Cypher. Cypher is the SQL for graph databases. It's kind of interesting because it looks like a combination of ASCII art and a query language. It's got some things that are similar here, but then it's got match and return, and it's got this weird looking structure here in the middle. And that's the ASCII art looking part here. If we look at it in greater detail here, we've got this room that contains a monster, our nice sentence with the transitive verb. And on the left here, we have a room. And you'll notice that it's using parentheses. It's round, like we draw our nodes when we draw them on a piece of paper, right? And it's got a label of colon room. And so this matches a node that has a label of room. And the R means assign it to a variable R that we can use later. And the same thing over here is the monster, another node. It's round, it's got the parentheses, and it matches the monster node and assigns to M. In the middle here, we have the contains relationship being matched, and we assign that to a variable C. But you got these square brackets now, and there's an arrow, right? It's got an arrow right here that's showing you the directionality. So we're saying match in the graph patterns where there is a room that contains a monster. And so it'll traverse the entire graph and return all the matches that match that pattern in the graph. And so this is how this graph query works. And so it kind of looks like what it's doing, which is kind of neat. Yeah, question? Or was that just a wow, that's neat? So that's the heart of Cypher are these matchers. Now there's a lot of other stuff that's involved in it, but that's the heart of it. So let's look at something really simple. Let's create a room. So I'm assuming we've already created a schema for our graph database or Redis data for our relational database. And to insert a record into a relational database table, we're going to use insert into rooms, the keys we want to set, and the values we want for those keys. So here we're inserting the statue room. Hooray! We can do SQL. The comparable query in graph to do this, it uses create and then a matcher. So we're saying create a node with the parentheses there, right there, with a label of room, and then assign it to the variable R. So we're going to create that node, give it a variable R for purposes of our query. And then on that R, we can set attributes. We set r.id equal to 1 and r.name equal to statue room. And so this is how we would insert. An interesting thing here that's different between SQL, or relational, and graph is the relational database has an ID and a name, and that's part of the schema. It's set up front. The graph doesn't have that restriction. If we wanted to say r.trapped equals true, we could add that as well. and we wouldn't have to put it on all of our nodes. And so these are it's kind of like a little more document oriented, right? All of these attributes are optional. They can be set or not. They don't have to conform to a schema. Graph is schemaless. But the create command, it's pretty straightforward, really. Create a thing and set some properties on it. So how do we read it? We're going to do create, read, update, and delete to hit all the CRUD operations here. So if we want to read a room from SQL, well, then that's the wonderful select statement. Select star from rooms where ID equals 1, or select ID common name. That will give us the particular room we care about. To do that query in graph, we're going to use a matcher. And so here we're saying match in the graph, in the entire graph, match the pattern where we have a node with the label of R and assign it to R, or a node with a label of room, and we assign it to the variable R. And then we're going to filter those results with a where clause, just like we did with our SQL statement, saying where the room r.id is 1. So just give us room 1. And then we're going to say return it, return R right there. So that returns that entire node. If we got rid of the where clause, it would return everything, just like it would with the SQL. So we shoved the node in, we've pulled it out. Any questions so far?
You're saying it would only it would return everything, even things that weren't rooms?
No, well, it would return everything that matches the expression. So if we got rid of this middle statement here and we say match R : room, it's going to return all the rooms.
Okay, that makes more sense.
All the nodes that have a label of room. You can actually, a node can actually have more than one label. So you can make it a room and a chamber, for example. And then you can say, well, give me the chambers or give me the rooms. And some things could be both. And so you can actually do multiple labels as well. Cool. If we want to update the rooms, this is where I think it gets interesting, because the SQL here, we say update rooms, set the name equal to statue hall. We're getting an upgrade. It's not a statue room, it's a full-blown hall now. And where the ID is 1. To do that in graph, it's the same match where. So the first 2 lines here are identical to the previous slide. But instead of returning them, we're going to set them, which is identical to the slide before that, right? So we're matching a room, setting it to R, filtering it so we just get room 1, and then we set an attribute on it, and this updates it. We update the name to statue hall. So this is, in some ways, is like the intersection of the 2 previous queries, conceptually, because we're using that set syntax again. And if we wanted to add a new field, we could, or a new attribute, we could also use set to do that as well. To delete a room, the scariest of all commands, delete from rooms where ID equals 1. That's how we delete rows from a SQL database, or from a table in SQL in a relational database. And here you want to make sure you have that where clause, or you're going to have a bad day. You don't want to delete all the rooms. And that's true with graph too, right? But here, once again, it's match where. It's again the same syntax. Match this pattern in the graph, filter it down with a where clause, and then delete the things that, all the nodes that we have matched. So instead of returning R or setting things on R, we're going to delete R. So those are CRUD operations. Make sense so far? Any questions?
It's a little easier to grasp than SQL because multiple parts of the SQL statement is changing, versus with this guy, only that last statement changes depending upon what you're doing.
Yeah. Well, we're going to see here, the matches can get much more sophisticated. So right now, because we're just dealing with nodes, it's simple. And I've deliberately done that, right? I'm building up to more complex queries. But I do still agree with you, because I think the syntax of the querying language is a little more intuitive. And part of that's because it's visual. Part of that, I think, is because graph databases are actually just more intuitive. We're just dealing with the things that we're dealing. I feel like graph databases are almost like object-oriented programming. It's like programming around nouns instead of programming around verbs. And so it's easy to get your head around the things. And so graph sort of represents very realistic relationships. Whereas, and we'll see as we get into this, how the relational database to map our dungeon is more complex than the graph database to map our dungeon. I did want to have a note on nodes here. I've been using this syntax, match r::room where r.id equals 1. But there is an alternate syntax you can use with your matcher. You can use curly braces. And then this looks just like a JavaScript object. ID:1, name: statue hall. And then that will match rooms. It's like a built-in where clause.
Is there a preference among
blocks.
those in the know, like for which way to write your matchers?
Oh, is there a preference on which way to write the matchers? I think it just depends on what you're doing. I think the where is easier to read, honestly. But there are times when matching with the curly braces, if you just got one field, it's not any harder. If you got 4 or 5 fields, it gets a little harder to read. And it also ands them. Because you're saying match nodes, the where, it's this and this and this. Whereas with a where clause, you can say where r.id equals 1 or r.id equals 2. So it's a little more powerful. But this matcher can also be used to create them this way as well, which is very convenient. It's like, well, I want to create a node with these attributes. I can say create node. Well, actually, that's the next one right here. Right? We did the set. Well, here we say create a room with these attributes. And the thing you'll notice here is I didn't put the R. That's not a typo. I don't need it because in here I need to assign it to a variable so I can set things on that variable. Down here,
anonymous object being created.
Yeah, it's already been done. And so I don't actually need to assign it to anything. And so I think for creating nodes with attributes, I like the second syntax better. And it feels like I'm setting objects. Like I kind of like JavaScript. I mean, I run the Columbus JavaScript user group, but it creates sort of it feels JavaScripty to me. And so it feels real intuitive. So these are alternate syntaxes that you can do as well. And as you get into the language, there's times when one works better than the other, right? But they're just 2 options. And I will use the other option here. You can see, in fact, I do that right here. Here we're creating a monster. I love the puns that just sort of come out of this talk. And creating a monster is just like creating a room or a treasure, except I use the curly brace syntax here instead.
I'm disappointed it's not a spawn versus a create. That's okay.
Yeah. And that would be kind of fun, wouldn't it? I should do like graph databases with the Rust, and then we could have Rust monsters. But yeah, it's create, unfortunately. Here we're creating treasures. Here I'm actually showing that we assign it to a variable and showing that you can mix these syntaxes up. So I'm giving the treasure an ID and a gold piece value, but then I'm setting the name. So you can do both. So these are all perfectly valid cipher.
How does, I don't know if it matters, but is your graph database going to treat that create as one operation, or will it create that value that you've specified in the curly braces and then set the name of it as a separate operation?
You know, I don't rightly know. The only thing I should know the answer to that question to would be Redis graph. But I don't actually know. Well, actually, I probably do. I can speculate. I can't speak for the other databases because graph databases, because you know implementations vary, right? But Redis is single threaded, and so by definition, any kind of mutation you make is going to happen in that one thread call. And so they might create it and set it, you know, as 2 steps in code, but from a developer's point of view, that's going to be atomic. But that has more to do with the architecture of Redis than anything else, because everything in Redis is atomic like that. Because it sort of has the JavaScript model. It has a single thread in there, and it's just responding quickly to events, just like your browser does with JavaScript. Or it's actually like the Windows messaging loop in Windows 3.1. If anyone goes that far back, it's that same single threaded, single process sort of thing. Good question. Okay, so this is what a relational database looks like so far. We've got rooms, treasures, and monsters, and we got some rows in them. Our graph database so far, we've got a bunch of nodes that are all isolated. They've got attributes and they've got labels, and so there's data here. But right now, we really haven't done anything with graph that we can't do with a relational database and vice versa. The only real difference is that the graph doesn't have a schema and the relational database does. So let's do something a little more interesting. Let's put a monster in a room. So if we want to do that with a relational database, we've got our room table, we got our monster table. What do we need to do? Well, we need to add a foreign key to the monsters table. And so we need to alter that table. And then we need to update that monsters table to set the room ID for that particular row. So here we're adding Alice to the statue room. So if we've done relational databases, we've done this stuff a million times. How do we put a monster in a room with graph? Well, we need to create that contains relationship. And so what we can do is we can have multiple matches in our cipher statement. We can match our room, assign it to R, and you see I'm using that curly brace syntax there. And we can match our monster and assign it to M. And then we can create a relationship between those two nodes with the create command. So we can match a couple things and create. And because these are variables, it won't create them. It'll just say these things exist, create this relationship between it because the relationship doesn't exist. And so that puts that monster in that room. And again, you've got that ASCII art thing going on, right? And it reads like a sentence, the room contains a monster. There might be a temptation to say, can I just do this all in one create command? Do I need to match the rooms first? The answer is no, you may not do this all in one create command because these will create duplicate rooms and monsters. Because you're saying create a node with the label of room and an ID of 1. And so we're going to create that. And then we're going to assign it to that variable. And then we'll create a relationship between those newly created duplicate nodes. And so our old nodes won't be related and our new ones will be. So there's a temptation to think that you might be able to do this. Doesn't work. I made this mistake when I first started getting into it, which is really the main reason the slide's here. Putting treasure in a room, alter the table, exactly the same thing as putting a monster in a room. We're just putting a thing in a room. And for put the treasure in a room with cipher, it's exactly the same thing again. Here we're matching a room, we're matching a treasure, we're putting a contains relationship. One thing I think is kind of neat here is that the label, the type of the label, the type of the relationship is the same for treasures and monsters in rooms. They're both contains, and it's not a problem. It could actually allow you to do queries that say, give me rooms that contain things, and I don't care what they contain. So I don't have a sample of this, but I could say, a room contains a node that doesn't have a label, and that will match all nodes. So that would give me all the treasures and all the monsters. So you can do queries like that as well with graph that are pretty neat. So here's our relational database so far. We got some one-to-many relationships, but it's pretty much the same. Here's our graph database. The rooms that are starting to contain things. But the rooms are still a little isolated. We'll get to that. Right now, we can do a little bit of munchkining and find the rooms with the best monsters and the best treasure. So if we want to farm all the XP, and we want to do that from graph or with a relational database, then we do a join, right? So we select from our select the fields we care about from the tables we care about, join them with that where statement to filter out, so we don't get the Cartesian product, right? So we just get all the rooms for the particular room. So we get a room monster, room monster, room monster sort of thing, and then we order it descending. That'll give us the monster with the most XP at the top of our list to give us a prioritized to-do list of which monsters we need to hit first to maximize our XP. And again, this is not an unusual pattern in SQL at all. In graph, if we want to farm all the XP, we can match a room that contains a monster. So now our match is a little more sophisticated. We're saying, I only want rooms that contain monsters, and I only want monsters that are contained by rooms. And then I can, instead of returning these nodes, I can return the properties on these nodes. So here we're returning the room ID, the room name, and the XP of the monster. And then we can order that return by whatever value we want, which is pretty much the same as what we're doing in the SQL. So instead of, before we were matching a room with an ID and a treasure with an ID, and then we're relating them, here we're matching that entire thing. It's walking that whole graph and finding every room that contains a monster. And then we're returning them all. We're returning properties on all of them. And then we order them. Does that make sense? Cool. I saw one person nod their head, so I'm going to go ahead and plow forward. If we want to get all the gold, it's very similar, right? Here again, we're doing that same join on the foreign key. And here for the graph, it's the same query again, matching a room that contains the treasure, returning the ID, the name of the gold piece, and sorting descending by the gold piece value. So we can do a little bit of munchkinging, but right now we haven't done anything with graph that we can't do with a relational database. So far, so good. So what, right? We're missing a key piece here, and that is the relationships between the rooms. I want to know what rooms are related to what rooms so that I can take paths through the dungeon. That's where the value's at. So to connect the rooms in a relational database, this is where we have to create a many-to-many relationship with the room to itself. And we do that by creating a connections table. And so this new table has the from room and the to room. And then we start inserting connections. And so we got this one room, this mapping table. Its sole purpose of this is to connect rooms together in one direction. And so this is actually one of the ones that gets hard to start thinking about when you're doing SQL, right? When you got those tables that relate back to themselves. Graph starts excelling in this scenario. To connect rooms with a graph database, it's actually the same as putting a monster in a room or putting a treasure in a room. We just have to create a relationship between those two nodes. So here we're matching room 1 and room 2 with IDs 1 and 2. And then we create a leads to relationship between them. And we're saying room 1, the armory, leads to room 2, the barracks, which makes sense in a sort of way. And that's it. In fact, we could even extend this. I don't have this on the slide here, but because we've matched room 1 and room 2, and we know we want them to point to each other, we could put a second create statement in here and say room 2 leads to room 1. We could do that as well, which would be nice and efficient, right? But the thing, this is no different than putting treasure in a room. That's very different from a relational database. This is where the difference really starts to show. So here's our relational database so far. We can barely see the dungeon. We've got our many-to-manys and our one-to-manys and all that stuff we just talked about. This is what our graph database looks like so far. This is where we came in. We've got room 1, the statue room connects to itself, and it leads to the barracks, and barracks go to the statue room. The armory connects to the statue room and vice versa. And then we got a one-way path from the barracks to the armory. I like to think of that as like a fireman's pole. It's like all the soldiers are sleeping in the barracks, and then, oh crap, there's something going on. Let's quick go down the pole and go to the armory, but it's a one-way trip. Right? So you can model that sort of idea in this dungeon. So now it's super munchkin time. Because we want to query paths through this graph database. And how would you do that? In a relational database, you really can't do that. I mean, you can, but you have to keep joining back to that table repeatedly for the number of relationships, the number of how long the path you want to go through. So you could query it for a path that's 3 long or 2 long or 5 long by looping back on that rooms table with the connections. But with graph, you can use a leads to relationship. You can use the star. And that says from room 1 to room 2, from any room to any room, hop over, matches room, matches multiple leads to relationships. So it will hop over multiple leads to relationships. So this room, so room leads to room, it'll match that. Room leads to a room that leads to a room, it matches that. Room leads to a room that leads to a room that leads to a room that leads to a room, et cetera, et cetera, et cetera, matches that to however many paths you have. Now, you might be thinking, if you're really paying attention or you're really sharp, you might have realized that I can go in circles in a graph all day. How does this not create an infinite loop? The answer is I don't know how it does it. I just know that it doesn't. The graph databases will shortcut that. And so they'll give you the path from every room to every room up to its maximum, right? There's a maximum over one. It's like, well, if we've looped back over this before, we're not going to go over it a second time. So it won't return those duplicates. It'll stop. But you can imagine that this is actually a rather, this is going to return a lot. You've got 20 nodes, right? This is going to return a lot of paths. Yeah.
Sounds a little bit like what we do when we do pairwise testing, where we try to find all the combinations and we try to find all the things that work together one-to-one so that we can test all those things individually, but not have to duplicate those relationships with the rest of the data set. And so it reduces. Sounds like it does something like that.
Yeah, I'm sure it does something like that internally. There's something it's doing. I don't know how it does it, but it won't create a loop. So don't worry about that.
Right. I had another question before.
Yeah, sure.
Can you also add attributes to a connection, to a relation?
Yes,
Because
you can.
Yeah, I'm probably jumping ahead, ain't I?
I touched on it very briefly. I don't show the cipher query for that.
Okay.
But you can do that. My instincts tell me it's an anti-pattern, or it's a smell. That's probably a better way to describe it. If I find myself wanting to add attributes to a relationship, it usually means that relationship's probably a node.
Okay. Yeah, I was thinking about
that's not guaranteed, right?
Yeah.
You know.
It could be the distance between the rooms that you say, like, okay, I want to have the shortest path.
Yeah.
Not just the number of nodes, but just also in length. Or maybe when I extend it to like a navigation program, like I want to avoid all highways or something like that.
Oh yeah. Well, see, that's just it, right? If the highway becomes a node, not a relationship, because then you can avoid it. Right? And the leads to, all of a sudden you've got a corridor, and that becomes the noun. And then, so, I mean, this is just a feeling I have. I haven't done enough of this in production to be able to say with authority that that's totally an anti-pattern, but it smells funny to me. And so I avoid it. And these are good questions. You guys are understanding what I'm talking about. So that means I'm doing something good. So this guy here is similar to the one, but we have these 1s and 3s. And so you can say, I want to restrict how far it will go. I don't want to take every room to every room maximum path. Just give me everything that's within at least 1, but no more than 3. So you can constrain this down a little bit. And so that'll let you do queries like find all the nearby rooms. I match room from room 1. I'm in room 1. And give me the rooms that are within 2 hops away. So all the rooms that are next to me and the ones that are next to them. And return a list of them. That's kind of neat. That's an interesting query. And I could, excuse me. I'm drinking soda. It's making me a little burpy. You can also use that with some where clauses and some other clauses to make more interesting queries. Here, I want to match all the rooms. I want to match. I have a match that matches the room I'm in, room ID of 1, that leads to 1 or 2 rooms away. There's the room that it leads to, and that room must contain a treasure. And so this will match that entire expression. So if there's a room that's 2 hops away, but doesn't contain a treasure, that won't be returned because it won't match this pattern. And then I can return the ID, name, and gold piece value of each of those rooms, order them descending so that I get the biggest value at the top, and then do a limit 1, which will give me the room with the most gold that's within 2 hops away. So that I, as the adventurer, can find the next, give me something that's kind of close, but worth my time. All right. So that's what that query is doing. You can query the longest path through the dungeon. Maybe you're a completionist and you want to hit every room. That's how I tend to play video games anyhow. And you can actually, we got some interesting syntax here that I haven't talked about, this P equals. So we're saying match this pattern, match a room that leads to a room. You know, take the longest path through that dungeon. Give me, you know, from 0 to as big as it gets. But capture that path and assign it to the variable P for path. It doesn't have to be P. And then I can use these functions and return information about that path. Like I can get all the nodes that are in that path, or I can get the length of that path. And I can even say as leng, I can rename these things. And then I can order this by the length descending. So put the longest path at the top and then limit that to 1. And that gives me the longest path through the dungeon. The path that's going to hit all the rooms. You could not do that and get the shortest path through the dungeon, right? Let's find the room with the biggest treasure. So one of the things you can do with matches is you can put a with clause on them and basically create variables that you can use later. So here we're matching all the treasure nodes and assigning them to a variable called max. And then we're using an aggregation function here to take all those treasure nodes and take the maximum gold piece value. We could do an average there instead, or a sum, or whatever we wanted to do. We're doing a max, and then we assign that as a variable. Then our next match is going to say, give me all the rooms and their treasure. Rooms that contain treasure. And then we can say where the gold piece value of that room is equal to the max gold piece value. Now, if there's 2 rooms that have the max value, this will return more than 1, which is okay. And now we've filtered down and we've got a list of the room or rooms that are tied for first place for biggest gold. And so then we can return the name of the room, the name of the treasure, and the value of the treasure. So now we found the room that's got the biggest treasure. Let's do the path to the gold. This is combining all of these things together. This is a little bit of a monster of a query. Right? Yeah. So here we're matching, again, that we're getting that max gold piece value at these first 2 lines. And then we're matching the rooms that have that gold piece value. And then we're saying, get the ID of that room and make that our destination. So now we have a room we want to get to. We want to get to the room that has the most gold. Then we can say, well, let's find the path from our start room that leads to the stop room. The start room is 1, that's the room we're in. And the stop room is the destination ID that we brought up from up here, which is based on the max gold piece value from up here. Now we're getting that path. We can say, what are the nodes to that path? What is the length of that path? And then sort it ascending by 1. So give me the shortest path to that room first, and then limit to 1. So this will then return the shortest path to the biggest gold from where I'm at right now. So pretty neat. Do you want to see this actually work? I'm going to prove that this is real and not just a bunch of slides. So I have over here a dungeon generator. Written in Node. Apologies. Let me embiggen the text here a little bit. I guess should be a little easier to see. So this is using Redis Graph. And I've got a whole series of dungeons. Like here's the dungeon. When you create a new dungeon, it generates it. It gets I've got a little thing called rando. It gets die 3 entrances and die 3 exits and die 20, 10 plus die 20 rooms. It gives the dungeon a random name. And then saves it and adds all these things to it. And as we add rooms, it just sort of works through the thing, generating random rooms. The dungeon has an exit and entrance to different rooms. The rooms have treasures and monsters. Like if we look at the room here, it has die 6 minus 3 monsters and die 8 minus 5 treasures. So that's how we determine that. And we give it a random name. And then we look at like the monsters. We determine how many there are. And if there's only one, then we give it a name because it's a unique monster. And if there's more than one, then we just say there's that many of them there. And random challenge. So it's just a big random generator. I got this name generator here that picks like a random. I'm using some library called the fantasy name generator for Node. Because that exists, because the internet has everything, and it wants like different names for different D&D races, and so I just put them all in there because I don't care. And they get different names for genders. I just put them all in there because I don't care, and I just get a random name. And then the interesting part that actually talks to the graph database here is, well, here's my queries. So create dungeon, set name, return, create room, set name, here create monster, and you see here they're templated. So I'm using $name, $CR, $XP, and I can pass those in as an object when I say execute, and it'll fill it in for me. So this is the Redis graph library that does this. And so, it's to avoid the cipher injection attacks, right? Just like a SQL injection attack. And then here's the Redis executor. And it just has the Redis graph client instance. And we've got a little execute and return statements here, and execute and return many that are just convenience functions to use the API, because we just really care about having a simple data set back. This is all out on GitHub. I'm going to use this to generate a dungeon, but I did a dungeon beforehand, so I'm going to show you that first. I'm going to do that with the Redis CLI. And to use the Redis CLI, I said it's graph.query, and then in strings your cipher query. And I'm going to say match the dungeon, return D. So that's going to match a node with a type of dungeon. Oh. That's not a secret. That's the default password for Redis. Now we'll do the query. Oh, I made a mistake. I got to give it a key. So the entire graph lives in a key in Redis. So graph.query, the key name, and then the query in quotes. And so here we've got our node D back for dungeon, and it's the Forgotten Caverns of Storndis. That was the randomly generated one. So, and I can actually match everything in the graph with match n, return n. That will just return all the nodes. It returned fairly quickly, but see, this is why I hate using the CLI for this. Because I keep forgetting to say graph.query. There we go. And then I need parentheses. I swear I know what I'm doing. There we go. So we got 73 nodes back. And so this one's got the label of monster. If we go back further, we'll see some that have labels of, this is a room, the vile warren, the big pit. Here we got a treasure. It's a chest of coins and gems worth 75 gold pieces. So this is a dungeon I generated, but I'm going to go ahead and regenerate it by saying npm start. That'll run my server.js and generate me a brand new dungeon. And then we're going to query it using a better tool. Redis Insight is a it's a browser for, it's a GUI for navigating, querying Redis. You can do simple things like just do queries, like I can do keys star here and give me all my keys. But for graph, it's really kind of sexy. you can select your graph keys, and I can say match and room, match r: room, return room. And here it shows me all my rooms and their relationships.
Wow.
So if yeah, it's really, isn't it nice? So like right here, we've got the Grand Jail. If I double click it, it'll show me that there are 92 semi-precious stones worth 150 gold pieces in there. If I double click that, it's not going to do anything. This is the Grand Stairs. Did it have anything in it? Might not. Not all the rooms have things. Oh, it's got 3 displacer beasts. Right. That doesn't sound fun, does it? And if I go ahead and match the dungeon, we will see that we have a new dungeon. So there's our dungeon, the Deep Caves of Odo. I always enjoy the randomness that comes with giving this talk. You know, I never know what we're going to get, right? If I click on that, we'll see that the Deep Caves of Odo have 3 exits and 3 entrances. It goes to the Musty Room, the Filthy Jail, the Abandoned Chasm, the Dusty Chamber, and the Narrow Defile. And the Narrow Defile goes to other rooms, and it contains Ungrud the Demon. There's the Cavernous Pit. It's got a couple critters in it too. 2 hill giants and 2 purple oozes, because that makes sense. So this is just a better way of navigating this. And this is, you know, I just generated this, right? If I go back here to here and generate another one, and then I reload this dungeon query, is now the gloomy castle of is it Bildea? Yeah, Bildea. So, but let's do some of the real queries, right? So you've got this this sort of the select star.star from graph, match n, return n. That just returns all nodes. Boom, that's everything in your graph. So that's an easy query. But we've got over here, I cheat a little bit here because some of these queries are a pain to type in. So let's get all the rooms that contain treasures. We talked about this one a lot. Room contains treasure, return the name of the room, the name of the treasure, and the gold piece value. If I do that from here, now this one's not returning nodes. And so this is going to return tabular data instead. So now we have the name of the room, the name of the treasure, and its value. And actually, we got 17 items. You see up here, we got the little node view. There's no nodes. This isn't visualizable. But this guy down here is. And so we can see all the nodes instead. So we got 2 different views that we can use. Let's do the shortest path to the most gold. That's what everyone's really here for, right?
We like
this is
gold.
that last query I showed you earlier. What's that?
I said, we like gold.
Yeah, I do too, right? That's why we game, right? So, and if we look at the shortest path to the most gold is from room 0, or from room 1 is in room 13. So let's see if we can see what's in there. If we go to the graph view, we can say that's room 1, which is where we start, because that's the beginning of the dungeon. There's the Vile Pit. It's got a pile of coins worth 1,600 and 6 gems worth 125. So I'm guessing it's the pile of coins that hit it. And so that ran in. Does it say how fast that ran in? I'm going to go ahead and I don't know how to see the runtime in here in Redis Graph in Redis Insight, but I know that we can do it from here. Whoops, not that. Because one of the things about Redis Graph is that some of these queries are expensive, right? I mean, there's a lot of permutations, and so there is a performance concern there, and so you do need to use it judiciously. But let's do graph.query dungeon dungeon. There's our query. auth foo bard. So it did it in 134 milliseconds. That's still pretty good for what we're doing here. Like it's literally going through every path that matches a room to any number of rooms, right? If we do like, let's do the one where we just say the longest path through the dungeon. And let's get rid of the limit 1. Just so we can see what that looks like. Dungeon. So that was in about 400 milliseconds, and it returned 9,042 or 43, actually 9,044 because no 43 paths through that dungeon. So it walked all the permutations. So it's not too bad. Now, admittedly, let's see, just for context, about this Mac. See if I can bring that over there. I've got 2.4 gigahertz, 8-core i9 processor, and 32 gigs of of screaming fast RAM, and a 1 terabyte solid state drive. So I'm doing all right. I got a fairly beefy machine. I used to not be able to run this on. I had an older MacBook. I had an i5. Had like 16 gigs of RAM, and so it would time out on me. But you can do the stuff remote too. But it's still doable on a local machine. But you can always run it on Redis Enterprise Cloud, which is another option. So I'm just trying to give you a feel for the performance characteristics of this. So that's what we got there so far. That's the demo. Anything else anyone wants to see in any graph queries you want me to try? Okay. So obviously the example I've given you is kind of fun and ridiculous and probably not what you're going to do for work. But there are plenty of practical applications for graph databases. The sort of the canonical example is for social networking, friends of friends of friends, right? That's a very natural graph relationship, right? Just showing the nodes are people, the relationship is follows or friends. And it lets you do queries like, well, find the people that your friends follow because that might be people you know. Or it's like, if there's a lot of paths from your friends to this other person, that might be someone you know. And Facebook does this all the time, right? It's like, yeah, this person is known by 10 of your friends. You might know them and they recommend it. They're using a graph database to do that. Genealogy is a domain that lends itself naturally to graphs as well. It's genealogy is just like social networks, but over the centuries. Sally begat Guy, who begat Luke, to use my mom and my oldest son as examples. Those are directed graph relationships. Transportation networks, we touched on that already. We said highways. The highway would be a node. Transportation networks are a natural graph. And if you add like bus stops and train stops and those sorts of things to it, then you can query those graph networks, those transportation networks, to find the shortest path to get where you're going. I like the logistics example. You can build a graph representing where all the produce in your store came from. So, you got nodes that are your farmers, you've got trucks, you've got warehouses, you've got trucks, you've got stores. And with a graph database, you could say, hey, this farm has some contaminated lettuce, because that never happens. And can you tell me, give me a list of all the stores that have lettuce from that farm, right? Or all the distributors, or, right? A more topical example is epidemiology, right? You could do, contact tracing is another kind of social network, right? And so graph databases are great for that, because those sorts of problems too. I would say if you have a small problem domain, like if you're not talking like billions of records, or, if you're not having millions upon millions upon millions of nodes, you could use this for almost anything, because in some ways I find graph to be more intuitive than like a relational database. And so if I had a small problem that was relational, I would consider a graph for that as well. I just wouldn't, like I said, you don't want to have, when you start scaling up the nodes, you start having these permutations, and it gets expensive, right? The number of paths through that graph goes up geometrically. Here's some resources to go check out if you want to learn more. They're a little Redis heavy, but it's because I work for Redis. Redis.io, you can learn all about the details of Redis. Redis Graph is at redisgraph.io. You can go download all the documentations there, some examples of how to use it. There's a Docker image that I'm using for Redis Graph. I actually use the Redis mod one instead, but Redis Graph works just great. If you're curious about the Cypher query language, you can go to Neo4j's website. They created the language and have actually made it open for everyone at opencypher.org. And I've got a blog post where I talk about Redis Graph if you want to read that blog post up on Redis's blog. So, and lest you worry about getting all these links, there's a QR code at the end that you can grab that has the link to the repo that has the code and these slides and everything. So, I work for Redis. We've got a Discord server. So go and check that out. I'm on there all the time. If you want to ping me, ask me a question. I like that our Discord server invite code looks like our game master has sneezed. This is like GM Kachoo. Just randomly one generated, but gosh, I kind of have to use it in this talk, don't I? We've got university.redislabs.com where we've got a bunch of free Redis courses. So on over a lot of the capabilities of Redis and some of the modules that extend it. And if you wanted to set up a Redis instance yourself with a Redis Graph and you want to do it the easy way, you can just go out and get Redis Enterprise Cloud and get a free 30 megabyte Redis database out there as well. Here's the QR code that totally doesn't take you to the Rickrolled site. I'm going to do that one of these days because it's just so tempting. But it just takes you to this URL here, and then there's a link to the slides and all the code that you just seen's out there. And then if you want to, send me a pull request, feel free. I will happily ignore it. Yeah. If you see something that makes the code a little better, I'll incorporate it. Sure, that'd be great. And that's pretty much all I got. Thanks for attending my talk. Give me a follow on Twitter, and all that stuff's out on GitHub. I got other repositories out there for machine learning talks and like that. I probably should plug. We just released another Redis AI video today. So if you go out to Redis Labs YouTube channel, I'll just bring it up here. youtube.com/Redis University. We got Redis AI from the command line and introduction to Redis AI.
Mine.
We know this guy. And then we got stuff on Redis search, all kinds of stuff out there. So it's actually a pretty good set of videos, all free, of course, because it's YouTube. So go check that out too. I'm trying to get my view count up to be more than anyone else's, and right now I'm neck and neck with Redis JSON. So please help me out.
Nice.
Yes, sir.
I said nice, very nice. Quick question. Is there any concept of like indexes in a graph database? Is there
no.
Any kind of performance tuning you need to do or manage or anything along those lines?
I mean, you can make, I'm sure you can make structures that are less performant than others, but there's no index, there's no concept of indexing. Redis search actually is baked in with it. So you can do text search on, like you can do full text search on the text values in a Redis graph, which is kind of cool, but it's not really indexing per se. It's just an extra capability. The performance I didn't mention this, but so Neo4j is sort of the 800-pound gorilla in the graph database space, and they have the most capable thing. They created the Cypher query language, so they're more capable as far as like feature complete than Redis Graph is. But Redis Graph's in memory, and so we get a lot of benefit out of that. And one of the things we do for performance is we use Graph Blast, which is a library full of linear algebra stuff that allows you to query sparse matrices. So internally, the graph, there's like 3 ways to represent a graph. One is you can have each node is a linked list of all the nodes it relates to. And that creates a lot of O of N operations because you're walking all these linked lists. The other way you can do a graph database internally is you can do it as a matrix, right? And but the problem with that is you can do it, and it's like, is there a relationship between this node and this other node? Yes or no? So you get this big 2-dimensional matrix of all the nodes and all the nodes. But every single time you add a node, that matrix doubles. And so they're fast, but they're not space efficient. And so once they get so big, you just can't keep it all in memory anymore. And so what Redis Labs does is we use sparse matrices instead. And then Graph Blast is the library that allows us to walk over those sparse matrices. And that gives us sort of a compromise. Some operations are O of 1 and some are O of N, depending on what you're trying to do. And I don't fully understand how the sparse matrices work. I just don't have that deep a knowledge with it. I know the other two make perfect sense, right? The linked lists and the matrix, easy to visualize. The sparse matrix, it stores only the ones and not the zeros, but there's more to it than that. I just don't really understand how they work. I know that that's the magic that makes it fast, and I can say those words. I have an idea of what that means, but I haven't actually gotten into the implementation of how it works I couldn't code it. I'll get there eventually. So that was a long answer to your question, but it's a great.
What was the name of that library that does the linear algebra?
Graph Blast. BLAS, and it's all uppercase. So
Thank you.
I think it stands for binary linear algebra something or other, but it's actually a library, a C library that you can incorporate in your applications. So that's what we do. So that's pretty much all I got slide wise.